Welcome back to our videos. Today we're going to have a look at a few examples for linear subspaces. And of course, I'm also going to show you how to actually write down the proofs, the formal proofs that something is or is not a linear subspace. Let's start with an example that is similar to one you've already seen, but we make it a little more elaborate. So let's say we have a set in R3, in three-dimensional space, and we want that to be composed of scalar multiples of one vector, 1, 2, 0, plus possibly scalar multiples of some other vector, let's say 2, minus 2, 1. And those lambda and mu are scalar factors in the real numbers. That whole set is contained in R3. And I claim that U is a linear subspace of R3. Now to see that, we need to go through all three properties of our theorem. Let's first check whether that set is empty, and to do that we usually check whether it contains the 0 vector, because even if it's not empty, if it does not contain the 0 vector, it cannot be a linear subspace. In this case, that's easy to see. For lambda equals 0 and mu equals 0, we get, well, 0 times 1, 2, 0 plus 0 times 2 minus 2, 1. That, of course, yields 0, 0, 0. So that is contained in U. And in particular, that means U is not empty. It does have at least this one element. So the first check holds up. Let's move on to the second one. And for that, we'll need to consider two elements in the set U and then prove that their sum is again contained in U. So let A and B be in U. Then there exist, let's call those parameters lambda mu and lambda bar mu bar in R, such that, well, both are contained in U. That means they both have this form here, so that there are parameters lambda and mu, such that we can write A and B as this sum here for certain choices of lambda and mu. Okay, so for A, we have A is equal to lambda times 1, 2, 0 plus mu times 2 minus 2, 1. And B is equal to lambda bar 1, 2, 0 plus mu bar 2 minus 2, 1. I'm giving those here different names because, of course, the values might be different. So please don't use the same name here. That lambda and that lambda bar will usually not have the same value. They might, of course, yeah, but there is a possibility that they don't, and we want to prove the general case. So we don't exclude that they might have the same value. Okay, let's have a look at the sum of those two vectors. Then, what about that? A plus B is then, well, we just take those representations here. And what we get is, well, that is lambda plus lambda bar times 1, 2, 0 plus mu bar times 2 minus 2, 1. Now obviously what we have here is this here is a real number, and this here is a real number. So the result does have the form required for you, which is real number times 1 to 0 plus real number times 2 minus 2, 1. Exactly that form we have here. So that means a plus b is contained in u. So that second condition is actually true. Okay, let's have a look at condition number 3 then. As above, we'll take one vector, let's call it A, and we call the scalar that we also need, we call that sigma, right? Because I want to have lambda for the representation of A. So let A be in U and let sigma be in R. Then as above, there exist lambda and mu in R such that A equals lambda times 1 to 0 plus mu times 2 minus 2, 1. And then lambda times A, sigma times A is sigma times lambda times 1 to 0 plus sigma times mu times 2 minus 2, 1. And again, these factors here are in the real numbers, so that sigma times A has the required form for being in U. And that completes our proof that U is actually a linear subspace of R3. Okay, so that's one possibility. And it's similar to an example we've already seen. Let's have a look at one more example where we define the subspace, the subset, in a different way. Now let's say we have a look at the subspace of R2. So we take all vectors x1, x2 in R2 that satisfy one condition, and that condition is x1 plus 2x2 is 0. Right? So we don't explicitly prescribe what the coordinates of a vector are, but we prescribe a relation between those two coordinates that needs to hold. Is that a linear subspace? And how can we prove it? And again, I claim this is a linear subspace, so U is a linear subspace of R2. And of course, I'm ready to prove that. Again, we first check whether the 0 vector is contained in U. And to check that, we just have to see whether the 0 vector fulfills this condition here. So let's just substitute the 0 vector in there. And we get 0 plus 2 times 0 is 0. Check. Okay, so the 0 vector is contained in that space, and that in particular means the set U is not the empty set. Now for the more challenging part, let's say we have two vectors, A1, A2, and B, B1, B2. Let's say those are contained in U. That means these vectors will fulfill that defining property of U. And that means for the coordinates of those vectors, the equation holds. So in particular, a1 plus 2a2 is 0, and b1 plus 2b2 is 0. Now let's have a look at the sum. We call that sum C. C is a plus b. We can compute that sum. That is, of course, a1 plus b1 and a2 plus b2. Now the question is C in U? What do we have to do? Well, we have to check the condition. The question is C1 plus 2C2, is that equal to 0? And we can find out by just substituting what we know. Well, C1 plus 2C2. Let's see. C1 is this expression here. So that's A1 plus B1. C2 is this expression here. So we get plus 2 times A2 plus B2. And now let's rearrange that a little. Of course, what we can do is we can arrange all the A parts and all the B parts together. And that yields A1 plus 2A2. So those are the A parts. And B1 plus 2B2, those are the B parts. And now we do know A and B are contained in U. So as we've seen above, A and B fulfill this equation here. So this is 0 and this is 0. And that's exactly what we have here. Right? So that means this expression is equal to 0. And so is this second expression here. So what we have here is 0 plus 0. And of course that is 0. So the condition is fulfilled, meaning C is in fact contained in U. So that's condition number 2. And condition number 3 works pretty much in the same way. It's even a little easier. So let's take a scalar, lambda in R. Let's again take a vector A in U. And as before, we know that A1 plus 2A2 is 0. Define C to be lambda times A. So C is lambda A1, lambda A2. And then we check whether C fulfills the condition that defines U. So C1 plus 2C2, what is that? Well, C1 is lambda A1. C2 is lambda A2. And of course, we can factor out the lambda here. So that's lambda A1 plus 2A2, like this. Yeah, remember that's one of the distributive laws that hold in vector spaces. So, well, what do we get? We get an expression that again has a 0 here. Remember, this is exactly this equation here. It's equal to 0. So we get lambda times 0. And of course, that is 0. And just to make sure that you know what we're doing here, this is actually the 0 vector. So what that means is, of course, C is again contained in U. And that completes our proof, showing that U is closed with respect to addition and with respect to scalar multiplication. So U is, in fact, a vector space. And of course, you have noticed that U is actually the solution set of this linear equation. And that's exactly where this will lead to, and we'll discuss that in one of the upcoming videos. Basically, the solution sets of linear equations, at least of certain classes of linear equations, are linear subspaces. and we can classify them with the properties that we'll introduce for linear subspaces. So, to dig a little deeper into that question, I'll see you in one of the upcoming videos.